Before we even start question number 25 on page number 161, we should know something about how to find the average value of periodic functions. For that, let's take an example. Let us assume that y is a periodic function of time. And to make the example more specific, I am going to draw the graph of how y varies with respect to time. So time is on the horizontal axis, y is on the vertical axis, and the variation is as follows. So that's the nature of the variation. We are going to assume that t is in seconds, and one thing you notice about how y behaves is that it can take one of only two values. It's either equal to 5 as it is over here or over here, or it can be 10, and it can't be anything else apart from 5 and 10. That's the first thing that you notice. The other thing that you probably notice is that y varies periodically with time, with a time interval of 2 seconds. So if you look at this particular time interval and look at the type of the shape which the curve has, now that same shape, it's more or less like this. That same shape is repeated again in the next 2 seconds, and so on. That's going to happen in the next 2 seconds also, although I have not shown it over here. So this is a typical example of a periodic function of time. Of course, we can even see how exactly y behaves. So for the first second, that is from t equal to 0 to t equal to 1 second, I'm talking about this part, it starts out at 5. So y is equal to 5, and at t equal to 1 second, the value of y suddenly shoots up over here to y equal to 10 seconds, and thereafter it is equal to 10 seconds right up to before t equal to 2 seconds, because at t equal to 2 seconds the value suddenly drops to 5 again, and this is one cycle. So the variation of y between 5 and 10 units, which occurs in 2 seconds, that is one particular cycle of this periodic function y. Now let us imagine a problem where we have to find the average value of y, and a particular type of average, the time weighted average. We want to find the time weighted average value of y, and we must now specify the time interval over which the average value is to be calculated. So I'll say that we want to calculate this average over a long time interval. Now if you really want to be mathematically very correct in this, you should be saying the interval delta t tends to infinity. But for practical purposes, we could take a sufficiently long time interval, and we could calculate the average value of t over that long time interval. The time interval is deemed to be sufficiently long if its value is very much larger than the time period of the periodically varying function, in this case 2 seconds. So what we want to do actually is the following. We want to find integral y dt from t equal to 0 to infinity divided by integral dt from t equal to 0 to infinity. That's what we really want to do. That's called the time weighted average of y over a time interval which tends to infinity. Now I will show you that this complicated appearing formula or integration, and in fact it's a ratio or the quotient of two things. It's done very easily by simply finding the time weighted average over one cycle. So what I mean to say is, if you start from t equal to 0 and up to t equal to 2 seconds, if you find the time weighted average of y over this time interval, then you automatically get the time weighted average over a very long time interval. You need not actually consider a physically long time interval. You can consider just one cycle. So let me first show you how to calculate the average over one cycle. So the average value of y over one cycle is, now it starts in the same way, integral y dt, but the top limit is now capital T, which is the time period, which is 2 seconds in this particular case, and divided by, now you have to divide by the time period. That's the time weighted average over one cycle. So let's try to calculate it in this case. Now integral y dt is nothing but the area, and remember it is the area over 2 seconds. So we want basically this area. So what is it going to be? It's the sum of two rectangles. The first rectangle has an area 1 multiplied by 5. The second rectangle has an area of 1 multiplied by 10, and down here you have 2 seconds. So the average value is going to be 5 plus 10, 15 by 2, which is 7.5. Now you'll get the same value of 7.5 even if you do the averaging over the next cycle. In fact, you should be able to convince yourself that you need not start at t equal to 0. You can even start at some arbitrary value like t equal to 0.5. In other words, I'm asking you to start the time interval here, and then of course your ending time will be at t equal to 2.5. You want to complete one cycle. So you should be able to convince yourself that over any time interval of 2 seconds, where 2 seconds is the time period of this periodically varying function, the average value of y is going to be 7.5. Now, why do I claim that this value, which I have calculated, it is the average value over one cycle, is also the average value over a very long time interval? So let's consider first of all, what is the average value, y average, over, let's say, 5 cycles. So naturally we are talking about a time period of 10 seconds. So the formula is going to be very similar to the one I've written over here, excepting that this is going to become 5t, that is 5 into 2, which is 10 seconds, and this is also going to become 10 seconds. So what I get is, you see, this is actually 15, isn't it? That's the area. It's this area corresponding to one cycle. So actually I'll show you the calculation that may be useful at a later stage. So it was 15, the area was 15, that corresponds to the area for one cycle divided by 2 seconds. So I got 7.5. Now what's going to happen if you consider 5 cycles is that the area is going to become 5 times. So 5. So in other words, what I'm saying is, you're treating this area plus this area, and like that totally 5 areas, the next one and the next one and the next one. So your total area is now going to be 5 times 15, and you're going to divide by 5 times the time period. So 5 into 2. In other words, this 5 and 5 will cancel, and once again you will get 7.5 as the average value over 5 cycles. Now the same thing will obviously happen when you calculate the average value over 6 cycles or 7 or 100 or 1 million cycles. Now consider any n number of cycles. So the average value of y over n cycles, the formula is going to be the same. It's going to be 15 n times divided by 2 seconds n times. So n will again cancel. I get 7.5. Now you calculate, you allow n to increase. So you allow n to approach infinity. Don't make it equal to infinity. Let it tend to infinity. So howsoever large a value of n we provide over here and over here, they are always going to get cancelled. So the answer is always going to be 7.5. So you know that when you increase n, you're essentially increasing the number of cycles, and each cycle is of 2 seconds. So when you allow n to increase very much, you have calculated the time weighted average over a large time interval, right? So it does not matter whether you calculate the average over a large time interval or over one cycle. The average value seems to be the same. The one cycle seems to represent the entire process, howsoever large a time interval you take. Now the doubt may arise, what happens if we consider a non-integral number of cycles? That is, you have a very large time interval. You want to calculate the weighted average, time weighted average over this long time interval, but you're not sure that it is an integral number of cycles. So the result is still the same. I can very easily show you that. So just look at this picture. So I mean the one which I have drawn over here, in which I am considering that the time interval under consideration is from t equal to 0 to t equal to this point. You can easily see I've called this time 2n. So that would mean that there are n cycles over up till this particular point. Remember, one cycle corresponds to 2 seconds, and the next cycle, you can have a look at this, is not yet complete. So it's a fraction of a cycle more, right? So I'll just call this something. This one I'll call t0, this time t0. Let me just clean up the figure a bit. So I want to calculate the time weighted average of y from 0 to t0, and the last complete cycle it's the nth cycle, it has got over at time equal to 2n, and after that in this time interval there is a fraction of a cycle, right? So you're going to use a similar formula. You're going to find the average. You're going to integrate it this way, accepting that in place of capital T I'll have t0, and here of course I'll have t0. So let's see what we get. You first realize that the integration can be carried out in 2 steps. I just split the summation into 2 steps. So I integrate y dt from 0 to 2n, and plus the further integration is from t equal to 2n to t equal to t0 y dt. I've just split the summation into 2, and this whole thing I now divide by, once again here I'll say 2n seconds plus, and the remainder is t0 minus 2n. So if you look at the figure, what I've done is, both in the numerator and the denominator, I've split each term in the denominator and the numerator into two terms. So one term corresponds to this time interval, which is an integral number of cycles, n cycles, and n is very large, and the other term corresponds to this fraction of a cycle. Now let's see what happens. Integral y dt from 0 to 2n is the area. It's this area plus this area plus this area. So it's as we said earlier, it is 15. The area of one cycle is 15 multiplied by the number of cycles, and from 0 to 2n we have n cycles. So the first term corresponds to n times that area. Just to complete the figure, the last cycle we are currently considering is this cycle, so that's the nth cycle. In other words, the first integral is going to be n multiplied by 15. That's the area of the integral number of cycles, plus, remember, there is some small area which we have left out, which corresponds to this integral, and essentially that is this area in the figure. Now that area, we don't know what it is because we do not know the exact value of t0, but we can say it is a fraction of 15. It definitely lies somewhere between 0 and 15. Now when I divide, once again I divide by 2n plus, now this t0 minus 2n is a fraction of the time period, so it's a fraction of 2 seconds. Now why I expressed it in this way, it will be clear when I do one mathematical manipulation. Remember, I am finding the average value of y, and also remember that n is very, very large. Now I divide n, or rather I divide by n in the numerator as well as the denominator. So in doing so, I am not changing the value of this expression, but this n goes from here, and I'll get upon n here, and this is also upon n. So it's fraction of 15 divided by n, I'll write it that way, and that's fraction of 2 divided by n. Now it's very simple. If you know the concept of limits, for those of you who know, you just take the limit as n tends to infinity, and you can easily solve. However, even for those who do not know the concept of limit, you allow n to increase indefinitely, make it larger and larger and larger. Remember, we are talking about a very large number of cycles, and n is the number of cycles. So what is going to happen is, compared to 15, this term, it's a fraction of 15, and further you are dividing it by a very, very large number like 1 million or 2 million, it's going to be negligible compared to 15. Similarly, this term, which is a fraction of 2 divided by a very, very large number, is going to be negligible compared to 2. And that's why, even in this case, the average value over, well, we actually want the average value over a large time interval, large delta t, that's going to correspond to the average value over one cycle, because it turns out to be 15 by 2, which is 7.5 again. So the moral of the story is, if you have a periodic function, remember that this logic works for any periodic function of time. Although we have taken a particular example, I am sure that you will be able to prove in a similar way that the result is true for any periodic function of time, and you are asked to calculate what is the time weighted average value of that function over a large time interval. Then you can simply find the average value, the time weighted average over one cycle. Your answer will match the required answer. Okay, so after this introduction of how to calculate the weighted average of a periodic function, we can now actually solve the question number 25 quite easily. So in this question, it is mentioned that there is a ball which is dropped from a certain height onto the ground, and the collision with the ground is perfectly elastic. Now at this stage, it is possible that you are unaware of what is a perfectly elastic collision, so you can actually ignore that term for this particular question. So there is a collision, you don't have to know what is a perfectly elastic collision, and they have actually described what happens to the ball after the collision. The ball rebounds to the same height from where it was dropped, and then again it falls. So it's a continuous process. The ball falls and it regains its same height again. Now what it means when it regains its same height is that in the collision there is no energy which is lost, either as sound or heat or something like that. So the speed of the ball when the collision was about to happen, that is just before the collision, if this is the ball, then that speed, let's call it v in the downward direction, and that's the floor. So after the collision, the ball is going to rebound with the same speed in the upward direction, and that is why it can regain its same height. In fact, that is what is a perfectly elastic collision. So anyway, I mean this happens because it's a perfectly elastic collision. So anyway, you can right now ignore those words. Now the ball is going to regain its original height, goes up, and then it's going to come down again in the same way as before, and once again it goes up and down. So basically it is a process which will hypothetically go on for infinite time, and it is a periodic process. So one cycle of that periodic process is when the ball comes down and it goes up again to the same height. Now this cycle is repeatedly going to occur. That is why it is a periodic process. Now you have to find what is the average force exerted by the ball on the floor during a long time interval. So what we will do, the first thing is, we won't calculate the average force directly by the ball on the floor, but rather by the floor on the ball. And then we can apply Newton's third law, and naturally the same force is exerted by the ball on the floor, but in the opposite direction. That's by Newton's third law. So we do it in this way. We'll find the average force by the floor on the ball. And secondly, since the average, it is an average force, and the force is a periodic function of time, because the entire process is a periodic process. So we can find the average force. Although we have been asked to find the average over a long time period, we can find it over the time period corresponding to one cycle. We can find the average over one cycle, and that will also be equal to the average over a long time interval. That is the result that we have just discussed. So what I will do is to just draw a sequence of events. What is actually happening to the ball? The ball is at some height from the floor, so that height, let's call it h, and this is situation A. The ball is at rest. Now the ball comes down, and just before it strikes the floor is going to have a downward velocity which I'll call v, and for clarity I'll show the ball not in the same vertical line but slightly away, Actually it should be in the same vertical line, but you can imagine that this photograph I have taken, I mean this particular picture is a separate photograph. So you have this ball about to hit the floor and its velocity is v downwards, and this is photograph B, or this is situation B. Now, as discussed earlier, in a very small time interval corresponding to the collision time, the ball's position is not going to change, but its velocity has reversed in direction, but the magnitude is the same. So this is situation B. Ball's velocity is v upwards, and finally, to complete the cycle, the ball reaches the same height as before. It is at rest, and this is situation D. And as I said, this is the completion of one cycle. The ball has gone down, the collision has occurred, the velocity got reversed, and the ball came up to its original position. So since there is a weighted average involved, I'm assuming that we want to find the time weighted average. So I'm going to draw a graph. Let F be the force exerted by the floor on the ball, and in the upward direction, of course. So the graph is going to be F, which is that force, versus time. And you're going to assume that situation A, that corresponds to t equal to 0. So at this point of time there is no force exerted, simply because there is no contact between the floor and the ball. Now ball A comes down and it travels to the ground. It's about to hit the ground, so we are talking now about situation B, and all the time the force doesn't exist, it's equal to 0. So this is the beginning of the graph. There is 0 force exerted. Now between B and C the collision occurs, and there is a large impulsive force, a positive force, because F is the upward force. So it's some variation. We don't know the variation over here, how it's going to vary. So we'll just draw some sort of curve. It goes up suddenly, and it's something like this, and then it comes down again. Actually this width should be very small as compared to this width. The collision time is very small, so I'll just modify it slightly. So that's the a better graph. And now the ball has started to rise, because we are now at situation C. Now the ball rises to the same height as before, and that means that we have reached situation D, which is of course the same as A, and the rise of the ball takes place in the same time as the descent of the ball. So this graph is going to be symmetrical. What I'm saying is, this is the time of descent and this is the time of ascent, and they have to be equal, of course, we know that. So this is one cycle which is over. Now if you want to gain more clarity, we can even draw the next cycle. So the next cycle starts at this point. The ball starts to descend again. So this part of the graph is going to be repeated. So there's no force for some time, and then suddenly the force shoots up. So now I'm repeating this part of the graph. The force goes up in the same way because there is contact between the ball and the ground. It comes down like this, and now I'm going to repeat this part again. So there is 0 force. So that's the second cycle. The first cycle ends over here, and we want to find what is the average force during a long time interval. We might as well find the average force exerted on the ball by the floor during one cycle, which corresponds to this time interval. That time interval we can call delta t. Now let's do the calculations. We can just consider how are we actually going to arrive at the average. So the average force over one cycle, F average, is integral F dt over one cycle. So I'll put the limits 0 to delta t, and of course I have to divide by delta t. Now the numerator is nothing but the area under the curve for that particular one cycle. So naturally I'm talking about this area. So to find this area, put it in the numerator. This integral corresponds to that area. And you know that integral f dt is nothing but the impulse. So you want to evaluate what is the impulse exerted by the floor on the ball during that first collision. Now you know that this is the impulse exerted by the floor on the ball during the collision, and during this collision there is one more force acting on the ball, and that is the weight of the ball. But weight is a non-impulsive force, and during the small collision time the impulse due to the weight is negligible as compared to this impulse, which is the impulse because of the impulsive normal reaction of the floor. And so this impulse can be considered to be not only the impulse due to the normal reaction of the floor, but also the resultant impulse acting on the ball during the collision time. And then, so that's the resultant impulse, and we know by the impulse momentum principle that the resultant impulse acting on the ball must equal its change in momentum. So the numerator we can replace by delta p of the ball in the upward direction. Of course we are maintaining our convention, divided by delta t. And the change in the momentum is the final momentum. Remember, we have taken upward positive, and the velocity after the collision is v in the upward direction, so the momentum must be plus mv minus the initial momentum is mv in the downward direction, so minus of mv minus mv divided by delta t. So you get 2mv divided by delta t. And you can use your knowledge of kinematics to find what is delta t. It's quite easy actually. When the ball, let me write over here, when the ball comes down, it rebounds and it goes up, and then it comes down again. And we are aware that the time between this event and this event, so I'm changing the cycle slightly, the time between these two events. So the ball, imagine that the ball is thrown up with a velocity v, it goes to the topmost position and then it comes down, and just before the collision it's traveling down with the same velocity v but in the opposite direction, the same speed v and in the opposite direction. Now we know that time is 2v divided by g, and we know that is nothing but the time between this event when the ball is released from a certain height and the ball gains that height again after colliding. The time is going to be the same. Essentially this time of descent is delta t by 2, and this time of ascent is delta t by 2, and the next time of descent is again delta t by 2. And whether you consider the process from this point up to this point, or whether you consider the process from this point to this point, the time required is still going to be delta t, the same. So we know that delta t is 2v by g. I'll just substitute it in the denominator. So what I get is the average force is 2mv divided by delta t is 2v upon g, and this turns out to be mg in the upward direction. So that's the average force exerted by the floor on the ball during one cycle, and that's also the average force exerted over a long time period, as we have discussed before. And then you apply Newton's third law. So the average force over a long time period by the ball on the floor will be mg, the same mg, but now in the downward direction. That's the answer given at the back. There is a second way to solve the problem, which is also quite interesting and maybe even a bit simpler. In this method, we calculate the average force exerted by all agents on the ball during one cycle. What I'm saying is we find the average resultant force on the ball. See, there are two agents which are applying forces. One is gravity, and gravity is always applying a force of mg in the downward direction on the ball, and the other agent is the floor, and the floor is applying a force in the upward direction, an impulsive force, and that's not continuous. It's only for small time interval when this large impulsive force is applied. So we don't even look at the individual forces initially, we just calculate what is the average resultant force. Now the average resultant force once again is going to be integral F resultant dt divided by, well, the limits will be 0 to delta t, one time period, and divided by delta t. I have not put a bar sign on top. I am considering the force as a vector. Sorry, I am considering the force as a scalar according to this particular sign convention. Upward is positive. Now the numerator, we can apply the impulse momentum principle. The numerator simply is the change in momentum of the ball during one cycle. And remember, the cycle starts at A and ends at D, and in both situations the ball is at rest. So the momentum change is 0 minus 0 and divided by delta t. So naturally it is going to be equal to 0. The average resultant force is equal to 0. So I think I'll just put this 0 over here so that I get more space here, right? You know the result now, that the average resultant force on the ball during one cycle is 0. Now I'll express the numerator in another way. The numerator is integral 0 to delta t. What is the resultant force? Is the sum of two forces acting. One of them is gravity, and gravity, since I have taken upward positive, the weight of the ball is minus mg, plus the other force acting is the force exerted by the floor on the ball, that's called F. So that's the resultant force at any point of time. You know, this F, sometimes it is equal to 0 when the ball is not touching the floor, and sometimes it's a high force, an impulsive force. So F is a function of time. Now mg on the other hand is a constant, so it's a constant function of time, one can say, minus mg dt divided by delta t. So we know that this is equal to 0. Just now we have seen that. So that means that integral, it implies that integral f dt from 0 to delta t divided by delta t is actually equal to minus of integral minus mg dt from 0 to delta t upon delta t. Now what is this term? This is exactly what we want to calculate. We wanted the average force exerted by the floor on the ball, and that's calculated in this way. So the result is the average value of the force by the floor on the ball is the negative of, now this is nothing but, you can either do the actual calculation by integration, it's very simple, this answer turns out to be minus mg, or you know that that's the average gravitational force acting on the ball, which you know to be minus mg. So the answer turns out to be plus. The average force exerted by the floor on the ball during one cycle is plus mg, which means mg in the upward direction. And now you apply Newton's third law. The average force exerted on the floor by the ball is mg, the same mg, but now in the downward direction. So that's another way to solve the problem.